invite me to give a seminar here. This is a really new thing where I saw this problem here. I mean, recently, a couple of weeks. This problem is exactly coming from some like discrete tomographies. The discrete tomography is talking about those, you have those convex tomographies, like the Funken's theorem. You have sections, this one will give convex bodies. Or you have projections, this one will give back to convex bodies. For example, you have some convex bodies, and its origin is symmetric. It is k equal to negative k. Origin symmetric. Then you consider out the projections and consider the volume. The volume projection must be equal. And Aleksandrov theorem, project theorem tells you that this will immediately give you k equal to L. So this is Aleksandrov projection theorem. And so it's, there are other things. For example, you change to the sections. It also gives you k equal L. And of course, you change to this to the boundaries. This also gives you k equal L. Those two are called Aleksandrov projection theorem. If you have a volume projection or surface area projection, it always gives you k equal L. And this is called Minkowski-Funk theorem. If you have equal sections, it will give you to k equal L. And furthermore, this one can lead to the Busemann-Petit problem. If you have less equal, then this will have less equal volume. And those thing is about the tomographies. It's called geometric tomography. You can always get information from the lower dimension informations. And now we'll go back to the discrete things. How about the discrete things? Those is convex bodies. And how about if you have convex bodies and you intersect with the integers? And this always gives you a polytope. The polytope is called convex lattice polytope. And this is using polytope because it's two-dimensional. It's called convex lattice polytope. If k is convex bodies, and you take the intersection with all the integers, and then take the convex form, and we'll go back to the k. And this is called convex lattice polytope. Definitely, this is a polytope. You cannot have convex bodies. For instance, you have some point like this. And you take the boundaries. This graph is exactly convex lattice. Of course, it's polytope. And the higher dimension is polytope. And those kind of stuff actually is not good because it discrete things. The discrete thing, if you have convex bodies, the first thing you want to ask that the Minkowski sum. And you consider Minkowski sum here, and you will find that one will not give back. Why? Because I mean, what's actually right here is like, if you consider this kind of things. You have like those lattice. You have another lattice. Add these two lattice with Minkowski sum is not again be a convex lattice or convex lattice polygon. Why? Because, for example, is that those kind of points. You're adding 2 points here. Sorry. For example, you're adding a point here. You have always like this graph plus this graph. This one. Sorry. When you're adding, maybe.
So K and L are no longer symmetric.
Sorry?
K and L are no longer symmetric?
Yeah, if it's even symmetric, it's.
In general, they're not symmetric.
Yeah, in general, it's not or just symmetric.
Yeah, okay.
Sorry, I've got the point. It's something like it will give back some point. Let me see. Sorry. Thought I have. Sorry, I thought I got the counterexamples. I'll show this later. But of course, if you have those, and another thing is if you double this one. If you double it, when you double it, it will give you. It's not also not inside because if you double this one, it will give you some point like this, and this one may be missing. So usually you can have some good relations in here. Not needed. Now I will present what the problem may look like. The problem may look like this. Now the problem is same as you're picking the one from there. I should for the upper one I should not using those one. I should use those. If you're adding this kind of point. Or if you're adding like this kind of point. For example, you have 2 points here. You're adding maybe this one. You have these 2 points. You're adding these 2 points. Okay, I'll give you this graph. Right? You only 2 points. And so you definitely have integer inside. Right? So always for simplicity you can have these 2 points here. And I have these 2 points here. Well, maybe not easy. Oh, I'll talk this later. Oh, sorry. Okay, let me see, go back to the programs. Go back to the programs. Okay. now you have those kind of schedule projection theorem. And Gardner-Gronchi-Zong. And they in their paper discuss lots of things talking about those discrete homographies. And in their paper they first talking about those slicing. But if you have two convex lattice sets and you take the slicings, if you take slicing, you always can find some line. It will be like how many points here will definitely immediately give you how many lengths here. So the length is unique determined by the number of points. So if you have two original symmetric convex lattice polygon, and you consider those intersect with integers, so you have equal, then immediately you get k squared. Of course, it's original symmetric. Convex lattice. Polygon.
I mean the sizes are equal, right?
Yeah, because the number.
Sizes.
The number.
Yeah.
This is a number. All canalities. If the number is equal, then the length is equal. The length is equal just by the traditional theorem you have k squared. So section is easy. It's much easier. But how about projections? We still have the original symmetric convex bodies. You consider all the projections. And you compute, you can put this in. And if you have those kind of equal projections, you compute the number of the projections. If they are equal, can it show that equal F? Of course, it's original symmetric. Because if you lose original symmetric is
Can you make the points thicker?
Sure. This is one. Another graph. They always have equal projections for every direction. But of course, this is not original symmetric. And you can generalize all kinds of things just by reflections. And so that's why you need original symmetry. And by the way, the original theorem, Aleksandrov theorem, it also needs those kinds of original symmetry. Otherwise, you can get counterexamples just followed by the cosine transform. Because the cosine transform only kills the odd part and left the even part. So you adding any odd part, it will give counterexamples. And now they ask that how about if you have original symmetric convex lattice polygons, if you still have this kind of result. And they found that they found counterexamples in 2 dimensions, not in higher dimensions. In 2 dimensions, they give a counterexample. I'll show you this one. And to talk about the counterexample. Actually, the counterexample is generalized by adding points for this graph. Why I talk this one? I'll show this is important later. So I think, a total thing. And you're adding point like this. You're adding a point here, adding a point here. Because order symmetric, has those points. Then reflections. One point here, one point here, one point here.
Now it becomes connected.
Another here. And some here. These three, believe me, these three have equal projections. And they two are original symmetric respect. These two are symmetric with respect to the this axis.
What did you say about projections? They have the same?
Okay, projection for every direction.
But it's not true.
No, this should be true. Why?
The middle has just 2 points horizontally.
Here?
No.
Horizontal?
Yeah.
1, 2, 3.
Ah, okay. I'm sorry. Yeah.
Because, yeah, I checked this one a couple thousand times. Here they have equal projection. These two are original symmetric with respect to this diagonal. Of course, it's with respect to this diagonal because they're original symmetric. And this one is not. But this one is itself is original symmetric with respect to these two diagonals. Of course, these 3 counterexamples, if you reflect to this direction, both. Those 3 reflect this direction. Give another 3 counterexamples, right? Just reflect. You consider some. If you reflect it, it's just adding points from here. Adding from points. Just reflect with respect to the y-axis. I'll give another 300 examples. So they said that the question they asked that if there are any other counterexamples except these 3 up to uniform transformation. What I mean by uniform transformation is that you have a transformation from Z2 to Z2 and with a determinate one or magnitude 1. This is called unimodal transformation. So the idea is how to prove this one. Is there other counterexamples? And recently I found that there are no other counterexamples. Because the time is limited, I cannot show all the proof. And the idea is just exactly from the picture of these three. Look at the picture of these three. First, those three are all parallelogram. Those three are all parallelogram, right? If you connect all the vertices, it will give you parallelogram. And the second, the first two are right-down symmetric with respect to some diagonal axis. And the last one is right-down symmetric itself. So I will show how to dealing with those kind of problems. Because when you go larger, actually when you go larger, actually it's good. Because more points will give you more information. And the idea is that I will show some key ideas. The first one. The first one is here counting numbers. And the first one, I mean the Aleksandrov projection theorem is considered width. So is there any relation between the width? I'm talking this one is the width of K and the direction U curve. So they have some U, and you have some convex bodies. Then this one give you the width.
What do you call it, weight?
Uh,
It means width. Width.
Width.
Okay, we understand. Width, right?
Yeah, width.
And this is now the Euclidean distance.
IDT.
WI.
Oh yes.
Yeah, this is
During typing, I forgot how to. And if you have those kinds of, it's just the width. And now, how about the relation between the width and if you have some points and you projection on this direction, and you counting numbers? So what's the relation between the number here and also the width here? That's the main case. And the idea is just using some kind of summations. If you have a K, and now, so how to get the width? The idea is if you have a K plus some like a plus minus U, using Mikau sum, and compute the volume.
This is an interval, right?
Here, this is some. U is U is belong to that two. I will give you all the details. This is important. Finally, U belong to that two, and we call U hat is a prime prime vector. It means that if U is equal to PQ, then there always exists a D is brightest divisor of PQ. And then U is one of the U hat PQ. The key idea is make these two coprime. And then if you have U hat here, and definitely U hat is still inside that thing. And now you're adding numbers. So you consider K, you plus Michelson, plus or minus U hat.
What does plus minus mean? This is the interval?
It's kind of, yeah, interval. U here, like U here.
Then you should write it as interval, I think.
You add the step.
It's okay, yeah.
Like that.
The front one.
Yeah. Then definitely there is a volume here. The volume is using the projection theorem. This one is exactly equal to the width of K and U first times. This is the length of the prime vector. Then double it plus volume K. You look like you just shift in this direction, one by U hat or another by negative U hat. So total volume is exactly the volume K plus the width times those things. So these projection theorems. And now, this one gives you a relation between what? Between the volume of this one minus volume K. Now we will think about the K ideas. What the K idea is, if you have K is convex lattice polygon, then here is not needed original symmetric. Then K intersect with Z2. This number satisfies so-called Peck theorem. Peck theorem tell you for any those kind of convex lattice set, you always have the volume, because the plus or minus sign always give you trouble. Volume K is exactly equal to number of the integers minus half the boundary points. And so on. Exactly gives this one. This is Peck theorem. And now we need to compare this one and this one. This one gives a width. How about this one? You just check these three terms. Negative one is nothing. You subtract, it cancelled. And this part. Half of boundary. Now you have those points on the boundary. And if plus a prime, plus a prime vector. The segment here don't have any integer point here, because this is prime vector. If it have some integer here, it's not prime vector. So same, for this segment you don't have any point inside. This for here don't have, for here don't have. So if you compute the point on the boundary, you have found you're only adding 4 numbers. So the difference between the boundary point will give you 2. And then the last one. The last one will like here. So the last one is K, if you K I should use those three. So the idea is finally we'll consider what's the difference of these two. What's the difference between these two? And you all found that the first one. The first one, the first one will have compute this one, and you go backward. Compare these two. And definitely this one is bigger. This is Minkow's sum. Minkow's sum of an odd case. And this is Minkow's sum of a subset of case. Right. So this is Minkow's sum of the odd case. And this is Minkow's sum of some point in case. So definitely this is bigger. So you have this concurrence, and you take the numbers, and they, backward. And definitely this is a great angle. So how about the difference of these two? You have some integers here, you have some integers here, and you adding points. For example, you have this 5 adding points. For example, in this situation, you have point here, point here, point here, and no more. And how many points you adding exactly give you the projections. Why? For any, if you have projections, you project into the U perp. If you have number, because this is U perp, you have boundary points, we'll project to here. You consider go back. And this direction is exactly parallel to U. Right? And if you add in a U hat, when you add in a U hat, definitely you create one more point. For any point you have projection, you always can create a new point. And that's why these subtractions will give you 2 times k projection you So for one, for you hat you get 1 point. For negative you hat you get another point. So each projection give you 2 points. So totally you get double of projections. Now plug everything back to here. And you will get width. I need a picture. And here, that's why I said the Minkowski-Zong of the lattice set cannot give a convex lattice set. Otherwise, the less than equal must be equal. And if equal, you can have these counterexamples. You will see later. Maybe. Now we just plug this one and pick a theorem back to this one. To compute the width. You have 2 times the width is of the U perp times U hat is equal to the V2. And exactly using the Pick theorem is equal to the difference of these 3. And then the difference of these 3 is exactly give you, if you have K intersect K plus minus U hat, and then intersect with Z2, this number, subtract K, intersect with Z2. This is first term. And then second term, minus, I already said the second term, the difference of the second term. The difference of the second term is exactly 2. So it's minus 2. And then using the inequalities here, this one is greater than equal. Let me see. This one is greater than equal. Greater than equal. The lower one. The lower one, if you subtract, is 2 times the projections. And minus 2. And finally,
May I ask a question?
yep,
You applied the Pick theorem, right?
yep.
What happened to the boundary term?
First time when you subtract, you only get 2. Because you only get 4 points more. Because if you have some here, I mean, it should be discrete. So you're adding points. You only, on the boundary, you're only adding those points.
Yeah.
No more. Because you're adding the prime vector. So finally, from this one, you get the projection is less than or equal to the width times the primary length of the prime vector plus 1. So what does this mean? If you have 2 Gauss bodies have equal projections, then the width cannot be too small.
So sorry, this is inequality?
Yeah, this is inequality. And the idea is to show, the proof, the ideal proof is show when the equal sign holds. Because you have more equal sign, you have more equal widths. You have more equal widths for the polygon. The polygon must be same. That's the idea. And first, there are a couple special directions. First is 1, 0 direction, 0, 1 direction. Of course, you can plus minus. But plus minus doesn't give you difference of the projections. This direction definitely is equal sign. I'll not prove it. This one is trivial because we project into this direction, and this is definitely equal sign. And there another is if you parallel to any edges, okay? If you parallel to any edges, okay, then it's equal sign. And this one is the exact proof in my previous paper, but the idea is not hard. It's parallel because k is orthogonal symmetric. No, here we need k is orthogonal symmetric. If k is orthogonal symmetric, you have one edge, definitely have negative edge. And consider the parallelogram. You have found for any k point here, you always can find a point here such that this one is parallel to you. This direction is you. For any point outside, you always have a point inside, such that these two, this is parallel to you. Because this is parallelogram. This length is you. You have a point outside, definitely you have a point inside. So it means that if you project k to U perp, the number is equal to the parallelogram project to U perp. The two must equal. And for this one, it's computable. And it's exactly equal to this one. Using Picker's theorem. Picker's theorem tells you that now we just remove what? You have the projections. Just you consider your head. Not necessary to you, just consider your head. The length of your head is enough because your head is the prime vector. For any point outside of you, it's a parallelogram. You always have a point inside parallel to your head. So when you have your head, you will have those kind of Picker's theorem. The volume of this one is computable. The volume is equal to the width. The width times U perp. So it's 1 equal to width times U hat. This is volume because it's parallelogram. And now you can how about the numbers? You can use the Picker's theorem for what? For this case. There's another part of the Picker's theorem. The volume is equal to the integers. The interior is inside, number of interior, plus the boundary, and then you must. This is also again Picker's theorem. The Picker's theorem before is the total number minus half a boundary. Now you remove all the half boundary points to here, then this becomes plus. So this all the interior all the points in the interiors and plus half the boundary minus 1. Real door. And now the volume is this one. And the weight of parallelogram is exactly the weight of the K. Another part, the interior points. The interior points of the prime, if this length is prime vector, then those points is all the projections. Yes?
Why did you change to plus again?
Sorry?
Why is it plus now?
Why is prime?
Plus.
Plus. The first one is the total number minus half the boundary. You pick all the boundary point to here. Then you have interiors, only interiors left. All the boundary points become here. And you see all the interiors will always be projections. So how many, if you consider the projection, now we need to compute the projections. Because this one is prime vector. So all points in the interiors, there are no other point in the interiors coincide in this direction. So when you have those projections, and immediately you will have those points, or will include all the interiors. And plus, what's left is the boundary. But for the boundaries, for example, you have key numbers here, then you have key numbers here. Now you project, you only have key numbers. So another one is half of the boundary. So the projection will equal to the interior numbers plus half the boundary. But the interior number plus half boundary is exactly fused projection. So you will have the width times the U curve is equal to the projections. And minus 1. Because, and previously I talked about any key outside point, you always have one point inside such that they have parallel, vector parallel to you. So all the points outside this parallelogram will have some point inside such that the projection is same point. And then this one is exactly equal to K, the projection of K. Minus 1. This one exactly gives you equal sign. I don't have time to talk all things, but this is one key step. A second key step is those direction is not. You have this inequalities, and you have equal sign of edges. So you have edge, the width is here, and if you have a different L, then the L should be outside or touch the boundary, cannot go inside, right? Because the width will always greater all the projections. So if you have equal projections, and if it's edge of K, and the width of L in this direction will always bigger. little bit bigger. And this is the K ideas. I don't have time to talk about it. I will show quickly the idea of proof. I thought I have time to talk about the proof alignment. But the idea of proof is like this. First, you have two orthogonal symmetric convex lattice polygons. And the idea of proof is, first one, you need to show that if they have projections same,
This is again the number of lattice points.
here is the assumption of the theorem.
This is the number of lattice points, not the.
Here are a number of them. Here are intersection of the number points. And if you have this one and one more, cannot choice, then KL must be some parallelogram. Only choice, parallelograms. And for this proof, the idea is break into two parts. There is one part if you have this situation, and this kind of graph is not true. You have this is the boundary points. You have this is the boundary of K, some edges of K, and you have vertices of L. This is L. This graph is not true. And why this is not true is based on my K lemmas. But the K lemma, I will talk for the K lemma later. But I first show the ideas. And this graph is not true. The second, if you have one edges, then you cannot, this is K, you cannot have some edge of L outside K. This is second, you should wide it. And third, and those two will immediately give you K and L. The boundary of K and L is alternating. What I mean by alternating is if you have K boundary here, you always have L boundary here. Those boundary is alternating. And this result will give this fact. And of course, together with this one in the case. Now, if you have alternating, you can show if you have alternating, then immediately you have this result. And why this is true is also based on the K lemma. I will talk about K lemma. K lemma is like this. K is orthogonal symmetric. Convex lattice, polygon, and if you have this is right triangle. So, for example, you have K here, and you have some right triangle T inside. So it's a right triangle. So if we have a right triangle inside of K, and you consider the vector of the edges. So for example, this one is with vertices is OT, VI and VI plus 1. Where VI plus 1 is the one edge of K. Then you have, if this one, VI plus 1, we call it is U. And if the U hat is equal to PQ, prime in the vector. And for all the direction, RS, if it satisfies this condition. If this is direction, of course you make it a prime vector. If it is prime vector, right, then it satisfies this condition. S or R less than equal to Q over T, less than equal to S over R times 2 SR plus 1. If it satisfies if it satisfies this condition, then you will have for any W is RS, and under this direction, K project on intersect that square, project onto W curve. The numbers is equal to W hat with, and actually not using W. It's okay. For example, at curve, at hat, W with K is at.
What's your key lemma?
Yeah, this is the key lemma. You have width equal. And do you have ranges? This one, it looks like it's not so good, but you can take this one to be 1. And this one is just 1 over 2 or 2 over 1.
Okay, so, yeah.
Let's have time to talk about the left.
Well, we'll have plenty of time in the break to, continue, that you can continue discussion with people. But for the moment, are there any questions?
Yeah, well, what about higher dimensions?
No.
I didn't understand how you used this inequality. How can you use that you have equality for all projections and use this inequality?
Because you have these inequalities. And also you have equality for the edges. And then it means that this one, also this graph is not true. And the only choice is this one.
So sorry, are there any results in higher dimensions?
No. None.
None?
None. No. Even because why? This is using Picke theorem. Picke theorem is you have a relation between the volume and projections. High dimension is called inherent polynomial. Inherent polynomial, you will have some polynomials. I mean, for the inherent polynomial, talking about like if your lambda k times lambda is equal to a polynomial of lambda with some coefficients. And the coefficient, the first coefficient is volume. Second coefficient is called the relative surface area. And the last coefficient is Euler constant. But rest of them, no one knows. And I asked some like commentaries, professors, they said that those numbers can be negative. So there are no geometric meanings.
Okay, yeah.
But do you have examples in higher dimensions at least?
Of course, no. No, even one counterexample is not known. So these three are the only counterexample for these questions. Or no, I mean. Of course, up to the reflections.
Okay, more questions? So we'll thank Ning again.